Swayam Prabha. Digital India. Educated India.
Okay, we'll begin. So in the last class, I was talking about vapor-liquid equilibrium for a binary mixture with regard to distillation. So distillation is an operation where you want to separate the components of a solution. Okay, when you have, let's say, a binary mixture A and B, and if you vaporize partly this liquid mixture, you create some vapor out of this, and then if you condense that vapor, and you will see the distillate will have a slightly richer in A than the original solution, okay, in one single step. And if you keep on doing it over and over, you can probably get pure A and pure B separately. Okay, so that's the idea. And we are actually thinking about designing distillation column for this particular process. And one of the key things that we need is to understand the vapor liquid equilibrium data. Okay, so how two components A and B are distributed in the liquid phase as well as in the vapor phase, and how we calculate them and how we make use of them for the design. Okay, like I said before, in any mass transfer separation equipment design, you need to look at equilibrium data, you need to look at the operating line, and then you need to look at the driving force line. Okay, these three things are very, very important. I was talking about this kind of phase diagrams, which you might have studied in chemical engineering thermodynamics. So here we are talking about two component mixture, mixture A and mixture B. We say mixture A is more volatile than B, meaning that the boiling point of A would be lower than that of component B. Okay, but if you have to say in terms of vapor pressure for a given temperature, you would see that component A would have higher vapor pressure than that of B. Okay, this is what I mean by more volatile or less volatile, so and so. What I have shown on the left hand side is at a constant pressure, we are looking at the relationship between temperature X and Y. X and Y are the mole fractions of component A in the liquid phase and the vapor phase respectively. X refers to liquid phase, Y refers to the vapor phase. I am saying only the composition of the mole fraction of only A, because I know B can be easily obtained by 1 minus X and 1 minus Y. So we don't have to explicitly show what is the mole fraction of component B in both phases. Having known X and Y, 1 minus X, 1 minus Y would correspond to the mole fraction of component B. Okay, so that is basically redundant. We don't have to really show that in this plot. So in this plot, I am showing T, X and Y. On the X axis, I have mole fractions. Mole fractions go from 0 to 1. Okay, so the X axis here is used for both X as well as for Y. So when I look at this X equal to Y or Y equal to X equal to 0, that is on the left hand side line, this corresponds to pure B. So this entire line that you see here on the Y axis, that corresponds to pure component B. On the other hand, X equal to 1 or Y equal to 1 on the right hand side, this line, this corresponds to pure A. So this is pure B. So we got pure B and pure A. So what this means is on the left hand side, you see there is this temperature TB, which refers to the boiling point. Okay, since I said pressure is constant, once you fix the pressure, the pure component will have a single boiling point. Okay, so that is denoted as TB here. On the other side, for the same pressure, pure component A would have a boiling point which is denoted here as TA. Okay, so these are pure component boiling points. Okay, we understand all of this for a single component. Now if I take a mixture, okay, between 0 to 1, the composition 0 to 1, you might think that there should be a straight line connecting TA to TB, as if there is one single boiling point for all these mixtures, but actually that's not the case. You are going to have range of temperatures in which the two components will boil, or the two phases will be in equilibrium. Okay, so you might have expected something like a line that goes something like this. Okay, you might have intuitively expected that I know the boiling point for A and boiling point for B, and then if I make a mixture of these two, there could be one line connecting these two, and those could be the boiling point for the mixture. Okay, that's what one would intuitively expect, but in reality that's not the case. What you would actually see is that if I take a particular composition, you have a range of temperature over which the two phases can actually exist in equilibrium. Okay, so this is a very, very important concept which is very important for this particular class. Suppose if I take this particular composition here, you see that there is a range of temperature in which the two phases can be at equilibrium. Okay, single components have a single boiling point. A two-phase mixture would have a range of temperatures, and that range of temperature depends on which composition you are talking about. When I am looking at a very small a and more b, that range is very narrow. When I go to this slide where I have more of a and less of b, again the range is different, magnitude wise, range wise. Okay, so that's very, very important point to understand. And again I also talked about the top curve which relates t and y is called the dew point curve, and the bottom curve which relates t to x is called the bubble point curve. So this is about keeping pressure constant and looking at how temperature and the two compositions are fixing this phase. Okay, so here you have fully a vapor phase, below you have a liquid phase, in between this loop bound by the bubble point and dew point curve you have a two-phase mixture. Okay, like I was saying before, if I take a point somewhere here, if I make a composition at this point, you will see it immediately phase separate into vapor phase and liquid phase. Okay, and the liquid phase will have a composition corresponding to this point x, y, x, and then the vapor phase will have a composition corresponding to this y. That's how you read this particular phase diagram. Choose a temperature and an average composition, it will split into two phases, and the two-phase equilibrium composition are actually read by the dew point curve on the bubble point curve. Now the same information I can obtain in other forms where I could keep the temperature constant and look at pressure and the two composition. So here I am just changing the story, I am keeping the temperature constant, but I am able to adjust the pressure so that I can go from single phase to two phase. In the pressure versus xy, you have the bubble point curve on the top and the dew point curve at the bottom, meaning the liquid here is on the top and the vapor is at the bottom. Again you have got a pure species vapor pressure Pb for the given temperature, and then you got a pure component A's vapor pressure Pa. Pa is more than Pb, that you can see here, for the given temperature, meaning A is more volatile. And then between this Pa to Pb, you see that there is a coexistence of two phases, vapor phase and liquid phase, both having component A and B. You have to make yourself very flexible and familiar with this kind of information, how to process Txy diagram, how to process Pxy diagram. They carry the same kind of information, but we are using different variables to characterize the phase diagram. Okay, are there any questions about this particular diagrams? Do you follow what I am trying to say here? So the x-axis is basically the mole fraction. Okay, so here there are three components x, y and p, or x, y and t. Okay, ideally I should be showing this in a three-dimensional diagram, but luckily here two of the variables x and y have the same range. So I am actually representing a three-dimensional diagram into a two-dimensional diagram by having a common x-axis representing both x and y. You see there are two curves here, the blue curve and the black curve. The blue curve here relates the temperature to the mole fraction, the vapor phase y. The bottom curve, black curve, refers to the temperature versus the liquid composition T versus X. So this kind of quite informative. We can look at where the single phase is, where the coexistence is, what's the temperature composition relationship, all that. But then when we actually think about distillation column design, we kind of map this phase equilibria into much more simpler way by looking at the relationship between only x and y. Okay, so how do I get this xy plot? Again, you have to make a decision whether you want to do this xy plot at a constant pressure or at a constant temperature. Let's say you want to keep the pressure constant because most of the distillations happen at constant pressure, atmospheric pressure, let's say. Okay, so we'll keep pressure constant. Then we are talking about the Txy diagram. right? So here what I can do, I can actually draw, I can take several temperatures between TA to TB. So TA, TB are the two limits in which the two phases will be in equilibrium. Okay, I can choose different temperature between TA to TB. For example, I can choose T1, T2, T3, right? And you see at that temperature there are coexisting vapor and liquid. Okay, for example, if you take temperature T1, there is a corresponding liquid phase composition X1 and the vapor phase composition Y1. X1 and Y1 are the equilibrium composition of the liquid and the vapor at temperature T1. Because I am fixing temperature T1 and the X and Y1 values are fixed, I collect those X and Y, X1 and Y1, and I plot it here. Okay, so this is Y1 and the below one is X1. You see, X1 and Y1, and this point implicitly refers to a temperature called T1. Okay, now let's take another temperature T2. Okay, so T2 is smaller than T1. Okay, and you can see that now the X2 value and Y2 values are now shifted to the larger values. Okay, so I collect these two X2 points and Y2 points. Remember, X2 I obtain from the bubble point curve, Y2 I obtain from the dew point curve. Okay, and those two are the points denoted in this curve. And similarly, I can take another temperature T3 corresponding X3 and Y3, and I can put it here. So you can see I can have very large number of points by choosing temperature from TA to TB, and then if I connect all these points, then I get this XY curve. And I also want to mention that this particular curve will be such that Y is always more than X. That's because A is more volatile compared to the composition in the liquid. The vapor phase will have more A, will be rich in A. So that's why Y is always more than X. To highlight this point, I have drawn a diagonal line here with at 45 degrees, so that you can see that the curve lies above the line. Okay, so here both x axis go from 0 to 1 and y axis also goes to 0 to 1. It's basically a square plot. Okay, both sides are equal length, and then it goes from 0 to 1, 0 to 1, and the point at this point here corresponds to x equal to 0. When x equal to 0, it basically means pure B. So here the temperature corresponding to this point would be the boiling point of B. Similarly, if I take a point here, x equal to 1 and y equal to 1, it's actually pure A, and that corresponds to temperature TA. Okay, so the temperature of this point varies from TA to all the way down to TB. We generally don't need a temperature when we do the calculation, so we just are okay with XY plot. But you have to remember, each point in this plot will have a different temperature. Okay, so this is for a constant pressure. I could very well make another XY plot where the temperature is held constant by choosing a pressure between PA to PB. PA, PB are the vapor pressures for a given temperature. Okay, since you are saying temperature is constant, you can look at what is PA, PB based on Einstein equation or vapor pressure data, and then you can collect various set of pressure. For each of the pressure, you can collect the XY values which are at equilibrium, and you can create another XY plot where temperature will be constant. So whenever you look at this kind of XY plot, you have to keep in mind whether it is for constant temperature or for a constant pressure. Okay. Now if I go back here again, here I have kept the pressure is constant. Okay, let's say 1 bar, and I have done this. Now let's say I want to do this for 2 bars. Okay, this curve will be different. So this green curve, which is a XY plot, will be also function of what pressure you are fixing. Okay, similarly, if I go here where the temperature is held constant, if I make an XY plot, that plot will also keep changing depending on what temperature you keep. Okay, so temperature is important, pressure is important, and its relationship to x1, y can be plotted like this. Or able to see the kind of information, same information, it's a VLE information, vapor, liquid, equilibrium information is plotted in different ways. So chemical engineering thermodynamics is all about creating or calculating this VLE. Okay, but we don't want to do it in full length, but let us take a very simple example. What's the most simplest thing we can do is to use Raoult's law and assume that the liquid mixture is ideal and the vapor mixture is also ideal. Okay, this is the simplest VLE you can get, and it's very easy to do it in an Excel sheet or with a pen and paper. Okay, so I'm going to demonstrate how to obtain this VLE data, XY data, TXY data, PXY data using very simple ideal solution ideal gas mixture, and then we will see how non-ideality kicks in, and then what are the complications that comes out when we have included the non-ideality. Okay, so let's first talk about what is the consequence of assuming Raoult's law. So Raoult's law says that at equilibrium, the partial pressure, the equilibrium partial pressure is equal to the liquid phase composition times the vapor pressure. Okay, so this PA star here is the equilibrium vapor pressure of component A, okay, exerted by a solution having composition X, okay, and PA is the vapor pressure which is dependent on the temperature. Okay, so this is one equation, and then we can see that PB will be what? What is PB? What would be the equilibrium partial pressure for component B? What is its mole fraction? What is the mole fraction of B? Simply 1 minus X, and its vapor pressure is PB, right? So we can define total pressure PT as PA star plus PB star, and this is nothing but XPA plus 1 minus X PB. And then you can calculate Y, which is nothing but PA star by PT. So since I am assuming it is an ideal gas mixture, the mole fraction is nothing but the ratio of the partial pressure of A to the total pressure. Okay. So we got equation 1, equation 2, equation 3 and equation 4. So here you can see the consequence of this. If I plot, let's say I am plotting Pxy, okay, let's say I assume temperature is constant, okay, I am looking at Pxy. Why I am saying Pxy? Because this Raoult's law relates the partial pressure and total pressure, so it's better to look at how Pxy are related, okay, for a constant temperature. The temperature enters in these equations only through the vapor pressure data, okay, because Pa, Pb are functions of temperature. If you change the temperature, Pa, Pb will change. So here let's say the temperature is held constant. You see this particular line here, this line is a straight line corresponding to equation 1, right? It says that as a function of x, the pressure of partial pressure of A, the equilibrium partial pressure of A will linearly dependent on the mole fraction, and the slope is determined by the vapor pressure. So this equation 1 here is plotted as a straight line here. Similarly, for the component B, it starts at PB here and then it goes to 0, okay. So that is equation number 2, and then I can also plot the total pressure, which is nothing but the sum of PA star and PB star, and that is equation number 3, also a straight line. So these three things come straight away from Raoult's law. Then I can also calculate the mole fraction Y in the vapor phase as PA star by PT, okay, and that is the curve that is shown here as blue line, okay, which need not be a straight line, which may be slightly a curved one, okay. So you can see using a Raoult's law, you can actually create a Pxy diagram like this, okay, where the partial pressures are linearly dependent on the liquid phase mole fraction X, total pressure is also linear, but the dew point curve may be slightly curved, okay. This is for the ideal mixture of the liquid as well as for the gas. So now let's say I want to make a Txy diagram, okay. So this is for a Pxy where the temperature is held constant. Let's say I want to use Raoult's law and create Txy diagram. Now we can follow a kind of an algorithmic approach. What we can do is, let's choose a first we fix a pressure, because when you say Txy diagram, pressure is constant. So you have to choose what pressure you want to work with, maybe 1 atmosphere, 2 atmosphere, 10 atmosphere, whatever it is, okay. You have to fix a pressure. PT is known or given. Now the first step you do is choose a range of temperatures, So how do we choose a range of temperature? Do we have a bound? What's the range of temperature we should be choosing? Between two boiling points, okay, from TA to TB. This TA TB depends on what pressure that you have fixed. If it is a atmospheric pressure, 1 atmosphere, TA TB would be the normal boiling point, but if you change the pressure, these will be the corresponding boiling points, okay. So you choose set of temperatures. Then the second thing is calculate PA and PB, these are vapor pressures for each of this temperature. So you may choose 5 to 10 temperatures here, okay, so that you have enough number of data points to plot the TXY diagram. So where do we get this vapor pressure from? So for many pure components, we can obtain the vapor pressure to a very significant accuracy through Ontine equation, okay. So this Ontine equation goes something like ln P is equal to A minus some B by some T plus C, okay. So this constants A, B, C depend on the chemical makeup of the substance species, whereas T here is temperature, P is the vapor pressure, okay. So if you look at any data book, Perry's handbook or thermodynamics appendix, you will see for a range of components these A, B, C values are given, you can take it, okay. So now I have chosen a range of temperature for my calculation. For each of those temperature I can substitute here and get the corresponding vapor pressure for both component A and B, right. So having known the temperature and the corresponding PA and PB, what we can do, we can go to this equation number 3 and we can solve for x, right, because PT is given, we are fixing the total pressure at which we want to calculate it, and PA, PB are known for each of the temperature, right. So we will solve for x from the definition of total pressure, which is PT is equal to x times PA plus 1 minus x times PB. If you solve for x, you will get something like PT minus PA by PT minus PB over PA minus PB. So since we know all these things, PT we know, PA, PB, we can PB, and then we can calculate what is x. Once you know x, you can calculate y from PA star by PT, which is nothing but x times PA by PT. Again, you can do this for all the temperatures. So essentially what you have done is you have chosen range of temperatures, and then you have got PA and PB from each of this for each of this temperature, and then you have got x, and then you got y. So now I got Txy, and I can plot Txy, or I can plot xy also, right. Now let's show you an example of this calculation. So I have done this for let's say I am looking at two components A and B, benzene and toluene, okay. So benzene and toluene are very similar, both are aromatic. Benzene ring, you know, toluene has one extra methyl group, but otherwise they are chemically very similar. Because they are chemically very similar, they can be approximated as an ideal solutions, and people have made measurements and they have shown that they follow closely the Raoult's law, okay. So we will take this as an example, and let's say I want to do this calculation for 1 bar. So at 1 bar, the boiling points for A and B, TA, TB are given in Celsius as well as in Kelvin, okay. So you can see that benzene boils at 80 degrees and then toluene about 110, okay. So they are very well separated in terms of boiling point, but they are chemically very similar. Then what I do, I go to this Ontine equation, which is given as ln P is equal to A minus B by T plus C, which I said already. And one thing you have to be very careful is that you have to look at what units are used, okay. The constants A, B, C values will depend on what unit systems are used. In this case, P is in bars and T is in Kelvin. So you have to stick to that choice of units. So you can see that I looked at some standard data book, and I found the value of A, B, C for benzene and toluene, which is got here. You got it here. So if you see that the boiling temperatures in Kelvin is about 353 to 383, Okay, that's a range of temperatures. So what I have done here, I have chosen some arbitrary temperatures ranging from 353 to 383. Okay, you can take more temperature if you like. So once you have this temperature, then I calculate the vapor pressure from Montaigne equation. So you see this is a ln P, so you have to take P equal to exponential of that term A minus B plus B by T plus C. So you can see that for each of the temperature I have I have calculated PA, similarly PB, these are vapor pressures. Then X, so X is nothing but, you see one is here is a pressure, total pressure 1 bar, okay, so it is there here 1 bar. So X is nothing but PT minus PB by PA minus PB, which I showed here. So you can find X values, okay, and then similarly Y values, which is nothing but PA star by PT, or you write X times PA by PT, you got range of Y values. So then what I have done here is, I have made two plots here. See here, you can plot T versus Y, that will be the blue curve, and you can plot T versus X, that is the black curve. You can see that it ranges from the boiling point of toluene to all the way to the boiling point of benzene, and in between there is a range of temperatures in which the two phases will be in equilibrium. Okay, so the TXY diagram. Now if I am not interested in temperature, I am interested only in XY, what I can do, I can go back here, I can, for each of the temperature there is a corresponding XY values, right, I can just collect those XY pairs and I can make this XY plot. When I look at this XY plot, I have to remember the pressure is 1 atmosphere or 1 bar in this case. Okay, if I change the pressure, this curve will be changing also. Okay, and each point in this curve has a particular temperature, that also you have to remember. Okay, follow? I will be sharing this Excel sheet for you to work around it. You can probably choose different components which are very similar, chemically similar, find their respective boiling points, find the on-time coefficients, and then just fill this plot, and you can generate set of VLE data. Not single material, a combination of two species, A and B, binary mixture of benzene and toluene. Okay. Okay, so what I am trying to say here is that you have a two-phase mixture. Okay, there is a liquid phase and there is a vapor phase. Liquid phase has two components, A and B. Vapor also has A and B, but the composition are also very different. So what I say is, I say that the mole fraction of A in the liquid is X. Mole fraction of B in the liquid is 1 minus X. Follow? Similarly, in the vapor phase, I say Y is the mole fraction of A in the vapor phase. 1 minus Y is the mole fraction of B in the vapor phase. So if I define X and Y, and I know the full composition of both phases. So here we are plotting what is the relationship between component A's mole fractions in the vapor phase and the liquid phase. If I take, for example, something like 0.5, it means that if I have a two-phase mixture with the liquid phase containing 0.5 mole fraction of A, in the vapor phase, mole fraction of A will not be 0.5, it will be much more than 0.5, which is actually about 0.7, right. This is happening because the two components are differently volatile. One is more volatile than the B, that is why compared to the liquid phase composition, the vapor phase composition will have rich volatile compound. Okay, that is a very fundamental idea behind distillation. This has information about benzene as well as toluene. Yes, is written in terms of more volatile compound, which is benzene here. Yeah, if I ask you to plot this for toluene, this curve will be just below this. Okay, because you will doing 1 minus X, 1 minus Y and all that. Okay, because in the case of toluene, the vapor phase composition will be lesser than in the liquid phase in this mixture. So this is what I have demonstrated here is a very simple idea that if you assume Raoult's law using vapor pressure data, you can actually get VLE data, TXY, PXY, XY, all that you can get. Okay, but in reality, the mixtures can be non-ideal, for which you have to calculate fugacities, activity coefficients, equate the chemical potentials, and then get the corresponding XY through iterative process, which you might have studied in thermodynamics. Okay, so let's go back again, and then From the gate question point of view, whenever people ask questions, they will say that the VLE data is not given and you don't have time to generate this kind of data in a gate exam. Okay, but there is a trick, there is a simple thing you can do, which is to invoke the idea of constant relative volatility. I defined a quantity called relative volatility, which is nothing but the ratio of the concentration ratio of the components in the vapor phase over the liquid phase. And let me first discuss for Raoult's law what is the definition of relative volatility is, and through that whether we can get XY data or not. Okay, so we are going another level of simplification, and we are going to say first let's start with the relative volatility. Relative volatility, yeah, it is denoted by a symbol alpha. It is defined as y over y by 1 minus y by x by 1 minus x, which is nothing but y times 1 minus x by 1 minus y times x. Okay, so this is a definition. This is an arbitrary definition. Okay, nothing sacrosanct about this, and this is very widely used in the context of distillation. So you can see that when we look at this equilibrium data, you see that the x and y are keep changing, and because of that the alpha will also keep changing. Okay, alpha is a measure of how the two components are different in terms of volatility. That's why it's called relative volatility. Okay, I also mentioned that if alpha is 1, it basically means both components have same kind of boiling points, they are same volatile. Okay, alpha is 1. But when alpha becomes larger than 1 or lesser than 1, you know that one of the component is more volatile than the other. So it kind of gives a measure of relative volatility. Okay, of course you can look at pressure vapor pressure data, you can make a sense of it, but this is how it is defined. Now let's say if I have a Raoult's law following mixture, what would be alpha? Okay, because for Raoult's law I already know how to write y and x expressions. We can substitute and I can see for Raoult's law obeying mixtures what is relative volatility is. Okay, so let's substitute this. What is y for Raoult's law? Y is nothing but x times Pa by Pt, isn't it? This is y. You can go back to this equation I showed before. Y is nothing but Pa star by Pt, or you can write Pa is nothing but x times Pa. So you will have x Pa by Pt, that is what this is. So this is y, and I keep x as such and x here, and then you have 1 minus x times Pa by Pt. So I can cancel x here, so I will have 1 minus x times Pa, and I can take Pt inside, I will get Pt minus x Pa. So what is this Pt minus x Pa? Look at your equations, see here we have written Pt is equal to x times Pa plus 1 minus x times Pb. I am saying what is Pt minus x Pa, which is nothing but 1 minus x times Pb. So we write alpha is equal to 1 minus x times Pa over 1 minus x times Pb, which is nothing but Pa by Pb. So for Raoult's law following mixtures, the relative volatility is nothing but Pa by Pb. So now let's go back to the problem I showed here, and what I've tried to do here is I try to calculate what is the relative volatility at each of those temperatures. You can see it starts from 2.6 and then it slowly changes, kind of decreases to all the way to 2.35. Why this happening? Because if you look at alpha, it is defined as Pa by Pb. Pa is the vapor pressure of A that depends very strongly on temperature. Pb is vapor pressure of B, which also depends strongly on temperature. But when you take the ratio, that ratio will not be very significantly affected by the temperature change. So even though the temperature is going from 353 to 383, but alpha value marginally decreases. Okay, so what we can do, we can say that let's take an average value of A alpha, and we say that relative volatility is constant. You can make that assumption because it is a very slow varying quantity. So here I have found an average value of alpha. Okay. So we are talking about two assumptions. We have a binary mixture which follows Raoult's law, also such a way that the relative volatility can be assumed to be constant. Like I said, this has a lot of consequences for the gate questions, because in many gate questions they will say relative volatility is constant and some number will be given. The question is, can you create VLE data with this assumption? Okay. Yes, we can do that. So we will go back here, assume that this is constant. At least in the case of benzene toluene, we seem to have that very kind of a close to constant value of alpha. So then if you look at this equation, if alpha has to be constant, we can actually write y versus x using alpha as a parameter, right? So in this expression, we have not made any assumption about alpha being constant or not. You are in luck if alpha is constant, then you can rederive this equation as y versus x with alpha being a parameter. Okay, so let us do that. So I take the inverse of this. So I get 1 by alpha is equal to 1 minus y by y and x by 1 minus x. So this is a very useful important relation that gives me y versus x data if I assume alpha is constant over the composition range. So typically in the gate question they will say alpha is given the constant value, and this is the equation you should be using to get the VLE data or xy data. So now let me see that if I assume this, how much will I be off from the actual calculation that I did for benzene toluene case. So what I do, I go back here, and since alpha is constant, I find y from the equation I just derived. Y is equal to alpha x by 1 plus x alpha minus 1. So you see that y values are here, okay, and I plot this along with the actual xy data I calculated, assuming alpha could be variable. Okay, so you see that here there are actually two curves which are almost overlapping. Let me see if I can zoom and you can see the difference. You see there are two curves, one is blue and another one is green, almost same on each other. Okay, so for Raoult's law following mixture, if alpha is nearly constant, xy data can be very simply obtained from this expression that I showed. So this is VLE data from constant alpha value. Very important from the gate point of view. So you don't have to memorize this equation. If you know the definition of relative volatility, you can very well just derive quickly in about a minute. Okay, so all right. So far we talked about ideal mixtures and how we can use Raoult's law to get VLE data explicitly or assuming constant volatility. But in reality, many mixtures are not ideal. They do not follow Raoult's law. Things become a little bit more complicated. Okay, so let me again walk you through some examples. I am showing some example of some mixtures. I think in this case, so on the left hand side, you are looking at PXY data for a mixture of carbon disulfide and acetone. Carbon disulfide and acetone, these are actually non-ideal mixtures. Why I say non-ideal? Because if I look at the partial pressure for CS2, okay, carbon disulfide, the straight line that you see here is predicted from Raoult's law, which I showed before. It's proportional to the mole fraction constant line, proportional to the vapor pressure. But actually if you measure, you will see that the equilibrium partial pressure is well above the Raoult's law prediction. So clearly it is a non-ideal solution. Similarly, if you look at acetone, which is the other component here, you see that this also deviates quite a bit from the Raoult's law prediction. The straight lines here are from the Raoult's law, the actual lines are shown here. Okay, this is for carbon disulfide and this is for acetone. So now suppose we add up these two pressure to get the total pressure. For Raoult's law, the pressure should have been a straight line. The total pressure should have been straight line. But you see, it is not a straight line for this mixture. You see that on the top curve is Pt versus X, that is the bubble point curve, and below you have Pt versus Y, which is the dew point curve. It kind of goes through a maxima. This maximum point is well above from both from Pb and Pa. What it means is that there could be composition where the mixtures are boiling at vapor pressure higher than the two pure component vapor pressure. Okay, so the consequence of this can be shown in the Txy diagram, which is on the right. You see that you should be getting the envelope between Tb to Ta in principle, but actually you see that there are temperature which is below Ta. Okay, these are called minimum boiling azeotropes or minimum boiling mixtures. Okay, so you see this is Ta, this is Tb. In the Raoult's law following ideal mixture, I showed that the entire thing was boiling between Ta to Tb. But for non-ideal mixture, you can have a situation where the boiling point can be much below the lowest of the boiling points. So we will say this is a minimum boiling mixture. And what is also interesting is that this happens because the mixture's total pressure goes above the respective partial vapor pressure. Consequence of that is that the boiling happens to be at lower temperature than either of the normal boiling points here. Okay, so point L here is where both the curves are touching each other, and this leads to what is called as an azeotrope. In azeotrope, the composition of the liquid and the composition of the vapor, they are basically exactly the same. Okay, usually we say A will be rich in the vapor phase than in liquid, but in this case when the two curves pinch, when they touch each other, the composition of the vapor and the liquid are actually the same. Okay, and what is the consequence of that? You see there is a point L, this is called the azeotropic point. On the left hand side, suppose if you boil a mixture somewhere here, okay, you will see it will phase separate such a way that the vapor will have more A than the liquid on the left hand side. Let us say you take another composition on the right hand side of this point L. So here you see the composition of the vapor is less than the composition in the liquid. So here the volatility have been switched. What was earlier more volatile has become less volatile and vice versa. And this can be also seen in the XY plot, where you see up to point L, A was more volatile because it lies above the 45-degree line, and after L it actually falls below the 45-degree line or diagonal line. Okay, so there is a switch, and this point is something that we cannot do distillation at. You can do distillation below or above, but not at that point. If you do at point L, you will see that both the distillate and the liquid will have the same composition. Okay, so this is called the minimum boiling azeotrope or minimum boiling mixture, and you can expect the opposite, which is called the maximum boiling mixtures or azeotrope. Okay, so here is another example. So I think this is for again acetone and chloroform. Okay, it's a mixture of acetone and chloroform. You see the opposite trend here. In the previous case, where the predicted the actual partial pressures were actually higher than Raoult's law prediction. Okay, they were actually positively deviating, but you can have things which is negatively deviating, meaning the actual partial pressure will be less than the Raoult's law prediction. Okay, for example, if you see here, this one shows, this straight line shows the Raoult's law prediction for ideal system, whereas the actual pressure falls below the line. Similarly for chloroform also. Okay, because of that the total pressure will go through a minimum. Okay, and this minimum can be smaller than the partial pressure of either of this. Okay, and in terms of Txy diagram, you will see that this is Tb, this is Ta. In the last example I showed the boiling happening at lower than the lowest boiling mixture, but here the boiling point can be higher than either of them. Okay, so you see this L point, boiling point, is more than that of TB itself. Okay, this is called maximum boiling azeotrope. In the XY diagram, you can see that it is opposite. From point 0 to this L, B is more volatile than A, and above L, A is more volatile than B. Okay, meaning if I boil a composition somewhere here, you will see the vapor phase will have more of B than A, whereas in this point, I will have more of A in the vapor phase than in the liquid. Okay, so everything is dictated or determined by the VLE curves. So for any given binary mixture, the way forward for us would be whether we have to consider this an ideal, so we can use Raoult's law. If it follows Raoult's law, can I use constant relative volatility and get XY data? That's the simplest route. Okay, if not, you have to look at this non-ideal models, get the VLE data, and this is a very key input in our design of distillation columns. Okay, so I urge you to kind of go through the textbook, take a look at all these pictures and try to understand what these pictures mean. Okay, how the data is presented. This is extremely important when we go with design of distillation column. Okay, so please read the textbook.